Alright, what's up? It is time for a Leetcode problem. I do this from time to time because I just like playing around on the Leetcode coding thing editor, and it's good to keep your programming skills, especially in the algo world, sharp, right? I don't think anyone would disagree, especially if you're in tech. So today I'm going to work on solving an easy problem, find all the lonely nodes. By the way, if you find my videos useful, if you think that they help in any way, yeah, like, subscribe, smash that like, as they say. And yeah, let's get to it. Alright, so let's read the problem. In a binary tree, a lonely node is a node that is the only child of a parent node. The root of the tree is not lonely because it does not have a parent node. Given the root of a binary tree, return an array containing the values of all lonely nodes in the tree. Return the list in any order. Okay, and so here's an example. So pretty much a lonely node is any node that has no sibling, right? So and it would also exclude the parent as well. So in this case, the top case would be 4, and it would be 6 and 2 in the next case, and then every other node here in this long legged tree, you could say, which is basically a list, right? um, is also lonely except for 98, 88, and 11. Okay, so pretty straightforward problem, I think. All they're doing is, when it comes to tree problems, and I picked this because I'm going to try to get progressively more difficult with these problems as I go on doing more of them. But this one should be pretty easy. All we have to do, so when I look at a tree problem, first thing I think is DFS or BFS, right? You want to do a depth first search or a breadth first search. And in this case, I think the easiest would be a depth first search. And a problem like this is almost like a template problem, right? So what I like to do first is create a DFS function node, right? And so the thing is, what we want to do, we need to know about the siblings of each of the nodes, right? So when you do a DFS, typically through a binary tree, you only know about in the standard DFS form, right? If you're doing a pre-order, post-order, or in-order traversal, the standard form is that you are only paying attention to the next node, and the next node has reference to its children. So in this case, I think what we'll need to do is we'll need to have a parent node. We need the reference to the parent node, and we need the reference to the sibling. Okay. Um, Now we can get the reference to the parent and we can get a reference to the siblings from the parents, but let's try it this way. And I'm going to make this a void function because I want to do this in a way where I'm passing in the list as a reference, lonely, and I'll be easily able to keep track of this in a recursive manner. So first, let's see, if root equals null, we'll return. Now if we have a null root, we just immediately base condition for the recursion is just to get out of the whole thing. So here's where the meat of it is, the actual inductive case. So if root, so I think what I want to do is I want to check for siblings, right? So first, but I also want to keep abreast of this condition. The reason that I kept the parent in there was that I want to make sure that the parent is kept track, like the parent is not alone. The root of the tree, absolute root of the tree, is not a lonely node. So we have to note if the parent is null, is not null, right? And if sibling equals null, and if the root, okay, so I think that's probably good. So if parent is not equal to null and sibling is equal to null, root, then we want to add to the list of lonely nodes. Lonely.add root, right? That val. Okay, and then basically what we want to do is we want to recurse through the tree. So DFS root parent root dot left because we're going to the now recursing to the children, right? And then sibling root dot right and lonely, right? And then we just reverse these, right? Root dot right and root dot left. So, why I like Python is that you can specify over Java, you can specify the arguments like left equals and right equals. It makes this kind of thing more clear. But basically what I'm saying is that we're keeping track of the siblings and we're also keeping track of the parent, right? So, the siblings are going to be the opposite of the current node. So if the main node that we're looking at is root.left, its siblings is going to be root.right. So then we do list integer lonely equals new array list, right? So we have that. Then we just do our DFS, and then we're going to start at the root. The parent's going to be null, right? And that's the main reason for including the parent, because the absolute root of the tree where we start is going to have a null parent and not be considered a lonely node. And then the sibling is null. Okay? So we start there. And I think then we return lonely. Return lonely. Okay? So let's try running this. DFS cannot be returned. Why not? Oh yeah, I forgot to pass the lonely list. Lonely. And not equal. So what's the problem here? That I applying to not equals, not equals, not. Okay. Minor mistakes. That's usually what you do. And then that looks like that worked. And let's try submitting the whole thing. And damn, that looks like it worked. Okay, faster than 100% of Java submissions. Memory usage only 89. Oh, less than 89.86. So doing pretty good on both ends, right? So basically, this is what the solution is to this problem. Okay, so there's some things to keep in mind, right, for those of you who are newer to coding. So the reason, there's two essential ways of doing this recursion. I could have also done this iteratively, but recursively I think is easier to see. Two ways to accumulate the result of the recursion. One is to pass the reference object through the entire recursive call. So in Java, remember, objects are passed by reference. So as long as the reference is passed to one function, every recursive function is going to have a reference to the original list. That makes it easy to append the original list. If, for example, I'm not doing that and I'm creating a new list every time, then what's going to happen is we're not going to be adding the elements to the same list. So this is just like kind of a quick and dirty way of doing this. It's kind of like a functional side effect. But it works in the case of this function, and yeah, so that's pretty much it. So that was a quick problem, and I'll talk to you tomorrow, and maybe get you a new one. Once again, if you like this video, like, subscribe, and if you have any questions, let me know in the comments. I think again this was pretty straightforward. There's lots of good resources on how DFS works. So yeah, all right, see you around.